In this video and the next video, I want to apply our knowledge of matrices and vector spaces to a well-known problem in statistics that's called the least squares problem. The idea is that you have some data of some y versus x, and when you plot the data, it looks like it's almost a line, but the y data has some noise in it, so you can't draw an exact line through these points, but you can draw an approximate line. So my daughter, who's 16 years old, actually had exactly this problem this week, and this is what she did. So she had the data from her chemistry experiment, and she just took her software and just drew a line, right? That's what she did, and said, that looks like the best line. So I told her, well, you drew that line, maybe someone else would draw a different line. You have to do this in some more systematic fashion so that it's reproducible. And that's what we're going to do here. Usually in statistics, what you do then is you find the distance between each of these points and the line, or a line that you may draw. And then you square the distances and sum them up. And then you try to find the line that minimizes the sum of the squares of those distances. That's why it's called the least squares problem. So that's what we're going to do here, but we're going to do it in a different way. We're going to do it from the perspective of matrices. So let me formulate the problem. So we have data. So the data I'll write as values of x1, y1, x2, y2. And then we have n data points, so the last data point will be xn, yn. So those are our data. And then in the standard sort of least squares problem, we're going to assume that the x's are exact. So the x coordinates of this data are known. That's considered the independent variable. And then the y's are noisy data. Okay, those are the dependent variables. Okay. So how do we formulate this least squares problem in a matrix sense? Even though we know the line cannot go through the data points, right? A line can only go through 2 points. If you have many points in a data set, there's no way you can have the line go through all the points. Even so, we can write down the equations. So if the lines went through the points, we can write down the equations. All we need to specify is the form of the line. So we're going to let our line be y equals beta naught plus beta 1 times x. Right? Beta naught is the y-intercept. Beta 1 is the slope of the line. So if this is our assumption for this purple line, then we can write down the equations. The equations would be the first data point would be y1 equals beta naught plus beta 1 x1. Right? So if this line y equals beta naught plus beta 1x went through this first point, it would satisfy this equation. The second point would be y2 equals beta naught plus beta 1 x2, and then so on. And the last point would be yn equals beta naught plus beta 1 xn. This is a matrix equation, so let me write the equation. This is the left-hand side here is a column vector. So this is y1, y2 through yn. Right? And the right-hand side then is a multiplication of 2 matrices. The unknown here is beta naught and beta 1. Okay, so we have some matrix here times our unknown vector. The unknown vector is beta naught and beta 1. And then this matrix is 1 times beta naught plus x1 times beta 1 equals y1. So 1 times beta naught plus x1 times beta 1 equals y1. So that's the first equation. The second equation is 1 times beta naught times x2 times beta 1 equals y2, and so on. So then we have 1 down to xn. Okay? So this is our matrix equation of this system of equations. This is what we usually call ax equals b, right? So let me just, our old notation would be this is the equation ax equals b. Okay, so we can generalize this. So what we want to solve then, we want to solve an equation ax equals b, right? This is the equation. Where the problem here is that there are many more equations than there are unknowns. There's only 2 unknowns, but there are n equations. Okay? So this is considered overdetermined. So this is overdetermined. Okay, so how do we do that? Well, we use what we've learned from vector spaces. So the product A times a column vector x is in the vector space of the column space of A, right? So AX gives you a vector that's in the column space of A. If AX equals B is overdetermined, that means B is not in the column space of A. There's no solution of this equation for the unknown x. The unknown x is our beta naught, beta 1. So B is not in the column space of A. But to find the best solution of this equation, what we can do is we can project B onto the column space of A. So instead of, we cannot solve this one, right? Cannot solve. Right? There's no solution. So instead, we solve the equation AX equals B projected onto the column space of A. Okay? And when we do that, we will find that the solution for x, which is our beta naught, beta 1, is indeed the least squares solution, the solution that minimizes the square of the distance between the data points and the line. Okay, we'll solve that in the next video. Let me quickly recap here what we're doing. So we have some noisy data. We want to fit a line to it. Okay, the x's are assumed to be exact values. The y's have noise in them. So we fit a line. We call the line y equals b naught plus b1 x. X is the x1, x2 values. Y is the y1, y2 values. This is a system of n equations. If we say that the line actually goes through these points, we get n equations. But only 2 unknowns. The only unknowns are beta naught and beta 1. So this is the system of n equations and 2 unknowns. It's overdetermined because there are too many equations, only 2 unknowns. So you cannot solve an overdetermined system. When we pull back our ideas of vector spaces, we know that B then is not in the column space of A. That's why there is no solution. So in order to find the solution, we need to project B onto the column space of A. That is what we do in this equation. It will turn out this is the equation we solve. And when we solve this equation, we'll have solved the least squares problem. Okay, I'm Jeff Chasnov. Thanks for watching. And let's solve this problem in the next video.